In this section of kinetics, we're going to be learning how to plot the data and determine order from experimental data. And previously I mentioned that you could solve for order either by using the algebraic form of the equations or the integrated rate laws, the calculus. The advantage of the integrated rate laws is that we can plot the data and using the line formula solve for any concentration, any time, as well as calculate something called the half-life, which we'll talk more about. So in this section, I'll be showing you how to treat the data and how to make the graphs. In class, you will be graphing one on your own, so you get to practice all of these things. Although there are more orders than 0, 1, and 2, these are the three most common forms of order with respect to one reactant. Right, so we can look at A going to product. Rate could be K times A to the 0th power. Let me erase that. A to the 0th power, which would be the same thing as rate is equal to K. We could have rate is equal to K times A to the first power, if it's first order, or rate is equal to K times A squared. Right, all three of these rate laws are possible. And so we have to graph our experimental data to determine if something is 0, first, or second order. If you'll notice, looking at the line, these formulas here, they are set up as y is equal to mx plus b. So in each case, let me just circle there, K. K is going to be slope. Notice that it's negative in 2. It's a negative slope in both the 0 and the first order. We also have something called T1 half, or the half-life. So let's define that. Let me erase for just a moment. The half-life is the time needed for 1/2 of the reactant to be converted to product. You'll see half-life used a lot of times in medication, so you know how to dose someone. Let's say a medication has a half-life of 8 hours. Like a lot of antibiotics, you would take the antibiotic 3 times a day, because 24 divided by 8 is 3. When you do this sort of reaction in the laboratory, you're going to set up a bunch of different tubes and let each one of those, in each one you're going to have some concentration of your reactant, and they're going to go for different times. So you're varying the amount of A and you're varying time. The only way to determine order is to do the experiment. Then we're going to take this data and our, in this case C4H8, we're going to treat it. That is, we're going to take the natural log of each data point for the first order plot, or we're going to take the reciprocal for the second order plot. Before we do any of the graphing, I want to first look at the 3 different plots and make sure and point out the features. This is the zero order plot, and in this case, we don't do any special data treatment to A. We just take the A concentrations on the y-axis and time on x. Notice that the slope is negative k, so that's our rate constant. All right, this brings up a good question. If we're doing 3 different plots for each set of data, right? One time it's going to be A versus T. One time it's going to be ln A versus T. And the third plot would be 1 over A versus T. How do we know which one is the right relationship? Which one is going to be the order of the reactant? What we're looking for is something called the R squared value. And this is how well the function fits the line. So what we're looking for, we'll get an R squared for each of those. Let me erase that real quick. We'll be getting an R squared for each plot, and the one that is closest to 1 is going to be the best fit. And that's going to determine the order. Okay, we'll look at some examples in just a moment. This is the first order plot. On this graph we have y is equal to natural log of A and on the y, and the x-axis is time. So in each case, time doesn't change. Time points are going to be the same, and we don't have to do anything to the data for time. We're only going to be treating the concentration of A. And here is the second order plot. Notice that y-axis is 1 over A, and the x-axis is time again. So it's the same set of data, A, but we're taking the reciprocal of each A data point. We also see a new term here that we need to define. A sub 0 is initial concentration of A, or another way to say that, A at the beginning of experiment when T time is equal to 0. And so you see the little 0 there. That helps us remember that it's initial concentration. Right, going over how to set up the graphs. Here's what we do step by step. We treat the data, and that is do the natural log and the reciprocal. Natural log of A, 1 over A. We set up columns in spreadsheet, and usually how I do this is I put in time for the first one and A, and then I copy time column and put in ln A data, or you can put the formula in Excel as well if you know how to do that. And then I copy time again and put in the data for 1 over A, the reciprocal. And so I have 6 different columns usually when I set this up in a spreadsheet. You highlight 2 columns at a time, so I would highlight the 2 here that would give me, this is the 0 order data set, this is the first order, and this is the second. So I would highlight the columns, and then I would insert chart, scatter plot. And so that first one's going to give me A versus time. And then I go ahead and I put the title and the axis labels. The more important part, though, is to add the trend line. And this is where we do the line formula. The y is equal to mx plus b. That is going to allow us to work problems. And we also show the R square. All right, so I'm going to show you some data, but we're not going to do any problem solving in this particular section. We will do that on the next video. In class, we'll go over how to do the graph together. I'll do another example for the class and then let you guys work through it on your own. Now, you should have done some graphing like this in lab, but that's okay. We'll work through it. All right, here's our data that we're going to be working off of for this first set of graphs. A is the concentration of C4H8, and then we're going to have a column for ln and a column for 1 over A. All right, so we'll just start putting this in the calculator. Natural log of 1, so depends on the type of calculator. Usually you put in the number and then hit the natural log button. In a graphing calculator, you have to put in natural log first, then the number, then enter. All right? The natural log of 1 is 0. Natural log of 0.894 is negative 0.112. Natural log of 0.799 is negative 0.224. Right. Natural log of 0.714 is negative 0.337. Next one, 0.638 is negative 0.449. Natural log of 0.571 is negative 0.560. Natural log of 0.510 is negative 0.673. Natural log of 0.456 is negative 0.785. And then the next one, 0.408, is negative 0.896. Natural log of 0.364 is negative 1.011. And then lastly, negative 1.121. Notice that the numbers get progressively smaller, further away from 0, and they're all negative numbers except for the very first one, which is 0. Then we go back to the original data set. 1 divided by 1 is equal to 1. 1 divided by 0.894 is equal to 1.19, and I won't write that in for all of them. I'm just going to go down the column. 1 divided by 0.799 is 1.25. 1 divided by 0.714 is 1.40. 1 divided by 0.638 is 1.57. 1 divided by 0.571 is 1.75. 1 divided by 0.510 is 1.96. I lost my place there. And then 1 divided by 0.456 is 2.19. 1 divided by 0.408 is 2.45. 1 divided by 0.364 is 2.75. And lastly, 1 divided by 0.326 is 3.07. All right, so now I have all of my data sets, and I would put in 6 columns into a spreadsheet. Remember, I'm just copying the time for each different y. So this is my first y, y1, y2, y3. And then we're going to make 3 different graphs. These particular plots, they lose some of the detail as you go from Excel to PowerPoint to explain everything. That's the app that I use to make these videos. All right, but I can go ahead and tell you what the line formula is. This is the 0 order plot. And the line formula for this one is y is equal to negative 0.0066x plus 0.9394. I know that r squared is 0.9762. Now remember that this is A, the concentration of A, versus time, and this is without doing any calculations with A. It's the raw data. Now as I look at r squared, this tells me that there's about a 98% accuracy with this, or fit to the line, if I were to convert that to a percentage. And so I'm looking, the closer we get to 1, the better the fit. And you can see that this is curved a little bit. It's not a completely straight line. So that's telling me that's probably not going to be 0 order. Right, here is the first order plot. Remember that this is natural log of A. That is really hard to read. Let me erase that there. Let's see if I can write it a little bit neater. ln A versus time. And usually, in a lot of these particular data sets, the time is seconds, but it could be minutes, days, years even. Right, the line formula, y is equal to negative 0.0112x plus 5 times 10 to the negative 5th. And the r squared here is equal to 1. And so unless I get a second order plot with an r squared of 1, I'm probably going to say that given the data set, this reaction is first order with respect to C4H8. But we'll go ahead and look at that second order data set. Right, lastly, we have our second order plot. Remember that the y here is 1 over A, and x is time again, and I believe this is seconds. And you can see just looking at the data that it is a little bit curved here. It's not as good a straight line as the first order data looked, but the line formula is y is equal to 0.0201x plus 0.8636, and r squared is equal to 0.9725. So this tells me, looking at the 3 different sets, we had A versus T, ln A versus T, and 1 over A versus T. These are all our possibilities: 0, first order, second order. For this particular data set, the answer is that it is first order. So when I write the rate law, let me erase for just a minute here. When I write the rate law, rate is equal to, now I know what K is from my plot, and it is 0.0112. It's the slope times the concentration of C4H8, and it's raised to the first power here because it is a first order dependence. So I know what the rate law is without having to go through the calculations that I would have had to for the initial rates method. So you can see there's an advantage to using the integrated rate laws and being able to plot the data. Right, I know this is a lot to show you one example here, but we're going to do another one in class together, and then you'll do one as well, one example while you're in class.